Look at a single, solitary object suspended in a dark void. We can easily identify its isolated properties. We can count its 300 pages, read the author's name, or note the red cover. But knowing those standalone traits tells us absolutely nothing about where this object actually belongs in the physical world. The moment we see the library, its placement makes perfect sense. It sits precisely between two other science fiction novels from the exact same decade. In any complex sorting system, the true meaning of an object isn't found in its isolated traits. It is defined entirely by its relationship to the things around it. Now, imagine a machine learning algorithm trying to sort a massive dataset, but completely failing to separate two distinct categories of information. Our standard human reaction to this failure is to assume we simply don't know enough. We think we need to go back out into the field and measure entirely new variables, like weight or color or temperature. Assuming that more raw features will inherently fix a failing model is a trap for data scientists. Dumping unengineered measurements into an algorithm rarely untangles the overlap. Most of the time, it just creates a higher dimensional mess of noise. This is where we turn to feature engineering. Instead of physically collecting new data, we mathematically transform the data we already have. Let's say you're trying to classify objects using only their height. On a single vertical axis, the red and blue categories are completely mixed together. The algorithm is blind. If you try sorting using only their width, you run into the exact same overlapping failure. But watch what happens when we calculate the interaction between these two failing measurements. Multiplying height by width creates a brand new mathematical feature: area. When we project our original data points onto this newly calculated two-dimensional grid, the overlap vanishes. The dots cleanly split into two distinct, easily divided clusters. We didn't take a single new measurement in the field to achieve this. We succeeded purely by intersecting what we already knew. The solution to a failing model isn't always sitting outside the dataset. Often it is hidden within the geometric intersection of your existing variables. In statistical learning, this trick is called basis expansion. It is a method used to achieve a more flexible representation of our data. This chart shows the raw speech frequencies of different human phonemes. At first glance, the top panel reveals a tangled, messy signal where the vocal categories overlap and blur together. To find the predictive patterns in data like this, AI engineers historically had to step in manually. They wrote explicit scripts to interact specific data points and force those hidden signals to the surface. Eventually, engineers built automated tools like polynomial feature libraries, which algorithmically map flat, raw inputs into these higher dimensional spaces. The job of a data engineer is essentially modern alchemy, converting raw, overlapping metrics into the exact mathematical signals an algorithm needs to succeed. While data scientists spent decades guessing and crafting these mathematical interactions by hand, modern AI scales this discovery process exponentially, and we call this evolution representation learning. A deep neural network's hidden layers don't require human intuition. They are constantly running millions of automated basis expansions, discovering complex combined features and geometric transformations entirely on their own. Advanced AI succeeds because it automatically learns the optimal way to represent and combine the data it receives. The answer to a complex classification problem is rarely found by collecting new evidence. It's found by finding the hidden connections within the evidence you already have. But all of this elegant math relies on a massive assumption. It assumes our library's original items were clean, legible, and ready to be sorted. In practice, the AI engineering pipeline looks very different. Before any algorithm can discover those hidden geometries, someone has to confront the untamed reality of missing values and completely unengineered data.